Hello class, I'm Dr. Yang and welcome to cs370 operating systems. Let's take a look at Linux scheduler. What I'm about to show you is the part of the Linux scheduler code. So essentially we are trying to look at the innermost part of the Linux context switch code. The code that I'm going to show you is abbreviated. I took this from the real Linux kernel code, but real the code has to deal with a lot more details. So the code I sort of abbreviated, so I just took out a bunch of stuff that is not helpful understanding the fundamentals of the context switch code. So that's one thing. Another thing is, I'm not expecting you to understand every aspect of this Linux scheduler code. My intention here is to sort of map what you just learned about context switch code into a real-world implementation. So one point that I'm trying to make by showing this is what you learned is actually used in real world in very meaningful way. Let me begin by introducing the TCB of Linux. Linux doesn't use the acronym TCB. Instead, inside kernel, you have this task structure. Okay? This is the equivalent to the TCB. By the way, the threading model that's adopted by Linux is this one, multi-threaded processes using kernel thread. So Linux has a kernel thread. So usually the thread is a manifestation of thread construct in kernel. So it's managed by kernel. In Linux, this task structure, it has a member of this type, struct, thread struct, and name of the member is a thread. And this is a substructure that saves a CPU-related context. As you can see, this is not a pointer. A thread struct is actually embedded, so there's a one-to-one relationship. But this task struct object has a member called struct, and the name of the member is mm. As you can see, this is a pointer, and obviously mm stands for memory management, and this is for address space context. So the instance of is shared among multiple instances of this thread task struct. So basically this captures the process address space idea, and inside this process you can have multiple threads. Therefore you can have multiple instances of the struct task struct. Each struct has to have a reference to address space, and that's why it has member struct. Right. Shown here, this table is the Linux thread state. These are the names of the state. And this is basically the mapping between Linux task state and textbook TCB state. And one interesting thing is we actually distinguished ready state and running state. We treated these two states as separate state, ready and running. But in Linux, they are all task running state. In Linux, the ready list is called actually run queue. This is a ready list. Let's say this is a head of run queue. And if you have a multiple task struct string like this, they are all in the task running state. But in Linux, the first one of the run queue is always regarded as the one that is running. So this is currently executing. This occupies CPU right now. And these are the threads that's not executing, that's in the ready state. All right, in Linux, it has three different waiting state. Task interruptible, task uninterruptible, and task stopped. Task stopped is the state that's actually put into waiting because it's stopped by user. And for most waiting, okay, the IO waits and synchronization waits, corresponding task states is task interruptible and task uninterruptible. The difference between these two states is that in task interruptible state, signal can wake, and task uninterruptible state, signal cannot wake. So the signal here refers to Unix signal, the system call that you can send by this kill system call. Okay, it's a confusing terminology here. But the signal in this context refers to the Unix signal, not the condition variable signal. The reason is, in some situation, if a thread gets stopped and somebody sends a signal, somebody called kill on you, and sometimes you need to break out of that wait, and the system call that blocked you should return. The blocking system call just returns with an error code. But sometimes signal cannot be delivered while you're waiting. In that case, this task uninterruptible state should be used. All right, let's move on. Let's take a look at the Linux context switch code. We are assuming 64-bit x86. The context switch code starts with this function. It will eventually call this switch2 function that requires 1, 2, 3 arguments. And this switch2 is actually macro. And it does some preparation that we are not going to talk about. And it then calls this switch2 ASM function. And this switch2 ASM is actually assembly code. So you have this switch2 ASM implementation here. This is assembly code. Before we talk about this assembly code, let's clarify some of these variables. The previous refers to the outgoing thread, and next is the incoming, and the last, we will talk about it in a moment, but this is the one after context switch. You want to have reference to the outgoing thread, but if you actually switched out, you lose that context as well. So basically this is there to remember it for you. Back to this switch to ASM. So according to 64-bit x86 calling convention, ABI stands for Application Binary Interface, and this is the standard documentation that defines all the calling convention and which register should be used in what context, and all the C structure layout and all sorts of different low-level C behavior that should be followed, and certain architecture and certain operating system combination, right? According to x86 64-bit ABI for Unix-like systems, the first argument is transferred by RDI register. The second argument is transferred by RSI register. With this, let's take a look at this context switch code here. I already mentioned these. As you can see, instead of push all D, Linux uses individual push instructions. And the reason why they don't use push AD instruction like here is that, first of all, 64-bit version of x86 doesn't come with the equivalent push AD instruction. And second of all, you don't have to save all the registers, because some of the registers are already saved by the calling convention. Certain registers get saved by the caller. You only need to save, in this case, the registers that hasn't been saved yet. So you save all these callee saved registers, and then you have this critical moment. Remember, the LDI refers to the outgoing thread, and RSI is the incoming thread. This task thread SP, this is just a number, so this refers to offset. Offset into the thread SP member of this struct, task struct. And RSP is the content of the current stack pointer value. So this is following AT&T syntax, so you're copying the content into this memory location. You're saving the stack pointer to certain field of TCB structure. Just like the textbook stack switch code, this is saving stack pointer. And the next instruction restores the stack pointer. So you read the value and update the stack pointer. So just like here, Linux does the same thing. And then you restore all the saved register. And you call this switch to C function. This is a different function. Look at this jump. It's not call. They are not using this call instruction. The call already happened at this point. So the return address has already been saved. and you execute the sequence of instruction that performs stack switch, and then just jump, not call, to this C function that handles the rest of the stuff, switch to. Switch to function is shown in the next slide here. As you can see, this is a previous and next, and it returns the outgoing thread's task struct. And everything fits together because this assembly code modified neither RDI nor RSI register. So we still have this valid previous and next function parameter, and that carries to this switch to function. So this prev p, the compiler will generate code using RDI to refer to this previous p and RSI to refer to this next p. So despite the fact that we performed context switch and we restored part of the register file, our reference to outgoing thread and reference to incoming thread is still valid. So this is still outgoing thread, and this is for incoming. The thing is, we still have some unfinished businesses regarding updating certain state of CPU and state of operating system. And these two instructions is needed to obtain special hardware context known as TSS. TSS refers to task state segment. The protected mode of x86 includes the notion of task that's recognized by the hardware. So x86 actually came with certain hardware version of the notion of context switch and task. But the thing is, most operating systems don't use this special facility, mostly because operating systems don't really want to use features that's only available for particular architecture. So for example, if you're writing an operating system, you want to make your operating system available to different architectures like ARM, Spark, MIPS, whatever. So in general, you want to reduce the amount of kernel code that is dependent on particular architecture because that hurts portability. And this is one of the reasons. But you cannot completely avoid the use of task state segment because the part of the field defined by TSS contains the base address of ring 0 stack pointer. So you have to obtain the current pointer that's being referenced by this CPU right now, and then you update the base address of ring 0 stack. And also this statement, you're updating this identifier that always has to refer to the current TCB. And finally, this returns previous P. So this is outgoing. Previous P is just the same thing. Okay, it returns to the TCB of outgoing thread, and it will come back to here. So switch to ASM returns essentially this previous value and saves to last. You may ask, why this indirection? Why can't we just use this previous here? The thing is, you're switching context. You switch the entire thing. So without this, after performing context switch, if you don't carry this information forward like this, then you lose the reference. The notion of previous from the perspective of incoming after context switch is not the outgoing one. It's the one that caused this incoming thread to switch out the last time it switched out. Okay, so it's confusing. Okay, but this is needed, and finally, whoever calls this context switch actually is able to retrieve who actually switched me in. All right, so we started out with this context switch code, this C function called context switch, and let's take a look at this context switch code. So this is what it looks like. So this is a context switch, and obviously it does something, and then it calls switch to, which we saw earlier. And the use of this switch to is interesting. So you basically have previous and next, and then this previous symbol. So this is needed as I said, after context switch, this code at this moment, after context switch, we know who was the last one, okay? Who switched me in. I mean, from the perspective of operating system, this and this is the same, but because of the fact that we switched context, we have to sort of come up with a scheme that forwards this information to this symbol after context switch. What about these codes? What it does is it switches address space if needed. You can switch to a thread that belongs to different process. So if that happens, then you have to not only switch thread, but also switch address space. And that happens over here. But what about these all if statements? This is needed to handle the case where you're switching to pure kernel thread. Remember, you have threads like K block D, something like this. This pure kernel thread doesn't have user length part. So for this type of threads, Linux kernel actually have all these kernel threads borrow the address space of whatever thread that executed before. That's safe because the address space that belongs to kernel is same to everybody. All processes share the kernel address space. So it really doesn't matter which address space you're going to use if you are a kernel thread. Previous may point to a different task before running for switch to 2. Okay, so I explained this just before. I probably should have said, absent this maneuvering, the previous is different. Without this previous probably points to a different thread. That's what I mean by that. All right, we took a look at this context switch code, and let's take a look at the code that calls this context switch code. And one prominent example is the scheduler. All right, so this is a very simple function, returns nothing, and you can ignore this preempt parameter. And what it does is it picks first the run queue that's associated with this particular CPU. So we're assuming multiprocessor SMP code, and eventually you pick the next thread. So you have this next. If your current one and the next one is different, then you need to perform context switch. Otherwise, no switch. And obviously, the sequence of these instructions are very critical. So you have to disable interrupt, and not only you have to disable interrupt, you have to grab the spin lock associated with this run queue. And eventually, you unlock the spin lock and also enable interrupt. So this performs both actions. So unlock the spin lock and enable interrupt as well. Over here, this is separated. So disable interrupt and grabbing the spin lock is separated because you need to perform this RCU note operation. So RCU refers to read, copy, update. This is some kind of advanced form of reader-writer lock that allows actually multiple reads without grabbing reader version lock. Yeah, but the thing is you need to do some special tricks. You need some kind of help from the scheduler to perform cleanup. So this is what this is. So grand scheme of thing is, in Linux, if you want to block, then you put yourself into some kind of wait list, and then you call this schedule function. And part of the schedule function, you get to perform context switch. All right, so this is the last slide. Since we looked at the gory details of not only just textbook context switch, but also Linux context switch code, let's tighten some of the loose ends. The last time I asked you a question when we were looking at the textbook context switch code, and there was a symbol or quote unquote variable name called running thread. Let's go back. Okay, this is the context switch code, and thread switch over here is the assembly code. And this reference here, running thread, this symbol refers to the TCB of the thread that is executing right now. And this running thread should point to the current thread. And after context switch, because we defined running thread should point to the TCB of the thread that's executing right now, the running thread should refer to this chosen TCB, the incoming TCB. But the thing is, we never updated any variable in between. So what gives? What is happening right here? That's what this is referring to, okay? What thread is currently running? So in Linux, the role that this running thread in our textbook example is served by this current symbol. And scheduler usually needs to find the TCB of current running thread. And on uniprocessor, you can just use a global. So you spend just a piece of memory, and because there's just one thread at any given time, after you switch thread, then just update that global variable with the new thread, and the subsequent reference to this global variable, you will get the current TCB. But on a multiprocessor system, it gets tricky to implement the idea of this running thread symbol. And there are many alternatives. One way is to just dedicate a register all the time to point to the TCB that's executing right now. For example, R29 in MIPS, by convention, just inside kernel, let's use this register all the time to refer to the TCB of running thread on this processor. And also, if hardware has a special per processor register, you can use it. The thing is, there's another solution which is quite clever, and this was used actually by Linux. I'm not quite sure if they still use it, but the idea here is that you embed a pointer to the TCB at the bottom of the stack. And this only works if stack size is fixed, which is not a big problem because in kernel you don't use a lot of stack. And this is clever because if you look at this and this is the bottom of the stack. So let's say this is the rock bottom of the stack. This is the starting point. We take advantage of the fact the outcome of context switch, you actually switch the stack. And we take advantage of this by you embed, sometimes you can embed the whole TCB structure at the bottom of the stack, but you can save the address to the TCB like this. So every time you want to grab the reference of current TCB, what you can do is you read the ESP value and mask off the bottom few bits. Usually the stack frames are aligned on page boundaries and multiples of several kilobytes. And by doing this, whatever value ESP you have, you get to obtain the base of the stack, and at the bottom you can find the pointer to the current TCB. Quite clever trick.